Hey guys, welcome. We made it to chapter 7 on periodic trends. But before we do that, I wanted to just give you a little bit of an overview of the trajectory of the course. Our last chapter was a pretty long chapter on quantum mechanics. There's a lot of concepts there. And those concepts are basically fundamental to most of the universe, basically as we know it, definitely central to chemistry, right? And in principle, we could have actually started the course with that chapter. But I like to start the course on the other chapters that we did, which basically were just introducing us to some general chemistry principles, getting us familiar with nomenclature, right? Naming uh, different concepts like the mole and different reactions, right? And also honing in our problem solving abilities. So in theory, we could have started with quantum mechanics because that's the basis of everything in chemistry, but we didn't, just for practical reasons, okay? But everything that we learn from here on out is going to directly tie to quantum mechanics. So it's really important that you understand those concepts on a very qualitative level, right? I don't obviously expect you to know all the math that goes into that. I don't understand all the math that goes into that. Or even to know why quantum chemistry is the way it is, okay? That is a very deep question, and people don't know the answer to that question. Einstein grappled with a lot of those questions, and so don't worry about that, but just keep in mind that everything's that we're going to talk about is based on those principles. And I think you'll be able to see in this chapter how things tie directly to quantum mechanics pretty easily. So now we can get started on this chapter on periodic trends. And basically what we're going to be doing is, we know from our last chapter that the periodic table is shaped the way it is based upon quantum mechanics and based upon electron configuration. It's basically an electron configuration map of the elements. And that's how you can think about it. And we also know that electrons give rise to almost all of the reactivity of the elements, okay? And so based on those two things, it kind of naturally follows that elements should have some patterns based upon how they're arranged on the periodic table, because they're arranged upon electron configuration. So the reactivity of elements, the chemical properties of the elements, has a lot of patterns when you arrange them in the order of the periodic table. Okay, as an interesting just kind of historical side note, Mendeleev, maybe you've heard of him. He's basically known as sort of the father of the modern periodic table. He did this work kind of in I believe in the 1860s or 1870s. And he was actually a chemistry teacher. And he, there's no quantum mechanics back then. This was before quantum chemistry came out. And he basically just started putting this puzzle together and seeing that, hey, there are some trends. And he predicted a lot of the undiscovered elements at that time, what their properties would be, with remarkable accuracy using these patterns, okay? So that's kind of a neat story. He's a very, very interesting guy. But anyway, we're going to be talking about 4 patterns on the periodic table, 4 periodic trends: atomic size, ionization energy, electron affinity, and electronegativity. So in this video, we're going to cover atomic size. And so atomic size increases as you go down the periodic table. You can think about this as, hey, you have larger energy levels. That's going to mean larger atomic size. Or more simply, as you go down the periodic table, you have more electrons. So that's going to give rise to, more orbitals and then just more volume, so bigger size, okay? And so you can see that, as you go down the periodic table, all of these atoms, this is a map of the relative sizes, are increasing. So cesium is bigger than rubidium, bigger than potassium, bigger than sodium, bigger than lithium, bigger than hydrogen. The principal quantum number, right, is going from 1 to 6 as we go down. And so our orbitals, our valence electron, our electrons in the valence orbitals are going from 1s to 2s to 3s to 4s to 5s to 6s, right, as we go down. And so that kind of makes sense. You'll notice that there's an opposite trend as you go to the right of the periodic table. The atomic size actually decreases. And that's a little strange at first. It's a little counterintuitive because you are putting in more electrons, right? You went from 1 to 2 electrons, or you went from 3 to 8 electrons as you went from lithium to neon. So what's happening here? It has to do with something called effective nuclear charge. And basically what this means is you're increasing the number of protons, okay? You're increasing the number of protons and you're not very dramatically changing the number of electrons or the orbitals that the electrons are in, right? When you go from lithium to neon, you're still in principal quantum number n. So you went from 2s orbitals to 2p orbitals, but those are roughly the same size, okay? And so you're still at the same roughly size orbitals. So you've added more electrons, yes. But what have you also done? You've added more protons. You've gone from 3 protons to 10 protons, lithium to neon. And that means you have a plus 10 positive charge in the nucleus of a neon atom versus a plus 3 positive charge in the nucleus of a lithium atom. And so what that does is it draws in the negative electron clouds, okay, the negatively charged electrons closer. When you have a neon atom, there's a 10 plus charge drawing in those 10 electrons much closer to the nucleus. And that makes their volume, okay, a lot smaller. Remember that almost all of the volume of an atom comes from the electrons. The nucleus is very compact in the center of the atom, okay? And so that's where this trend comes from. You can also look at the size of various ions, and it's particularly interesting to look at isoelectronic ions, so ions that have the same electron configuration. So let's look at O2 minus, F minus, sodium plus, and magnesium 2 plus. All of those have 10 electrons, right? All of those have the same number of electrons as argon. They have a bracket argon electron configuration. Oxygen only has 8 protons though. Fluorine only has 9. Argon, not shown here, has 10. Okay, sodium has 11, and magnesium has 12. So they all have the same electron configuration. So if protons didn't matter, they would all be the same size, but protons do matter. Magnesium has the greatest effective nuclear charge. It has the greatest number of protons. So that's going to suck in those electrons the most, and magnesium 2 plus is going to be the smallest out of those 5 we just mentioned. Aluminum would be even smaller. It has, 1 more proton, right? 13. So that's sort of how this all works. When you have isoelectronic ions, the ones with the greater amount of protons are going to be much smaller, okay? And that's consistent. I don't think there's any exceptions to that for ions, isoelectronic ions that are known, okay, under the same circumstances and measured in the same way. So that's what this says here. Fluoride and sodium ions have the same number of electrons. They're isoelectronic, but sodium has more protons, hence it's smaller. So a very simple practice problem would be rank the following in terms of increasing size. There's your periodic table. We're given potassium, bromine, and nickel. These aren't ions. These are just neutral elements. So let's look. All right, we got potassium is here, number 19. We have bromine, 35, okay? And then we have nickel. Well, look, they're all in the same row. So the trend that I care about is that going to the right on the periodic table makes atoms smaller, okay? And so which one's the furthest right? Well, that's bromine, so that's gonna be the smallest. And then nickel's in between, and then potassium. So it's basically as simple as that, guys. I'm not gonna give you tricky problems like what is bigger, sodium or calcium? Well, you went diagonal on the periodic table, right? And so, which trend weighs out? Does the downward trend beat out the across trend? That's hard to predict, okay? So I'm gonna give you very simple ones, roughly in either in the same column or in the same row, okay? And that's how this will work. All right, we'll continue talking about the next trends in the next videos.